Sudipto is one of those people who has constantly reinvented himself. So he was a PhD student in Stanford, did really influential work on approximation algorithms. If you have a linear program relaxation that you need rounded, Sudipto is your go-to guy. He then did a postdoc at AT&T, and at UPenn he kind of did important work in data streams. Recently he's been doing very influential work on approximation algorithms for multi-arm bandit problems. So without further ado, succinct representations and efficient algorithms based on linear program.
Thank you, Andrew, and thank you everyone for waking up and on a 4-day long conference. I would be talking about succinct representations because I'm told that that was the innovation of this entire workshop, that it was succinct. The talks are not necessarily that succinct. So this is joint work with Kokche Nan, who is now in Google, and the paper is available in archive at this number. Okay, so what I want to start with talking about is optimization is intimately connected with the representation you start from. And this is something we know, this is something we've always seen in undergraduate textbooks. The particular problem I would talk about in this talk is a linear program, which is a simple maximization problem. It's a packing problem. If you see, that feels like I am packing A times X to be less than or equal to B. And I would assume all the numbers involved, A, all the vectors, C, B, are all positive. There is a term for this. This is known as positive linear programming. Okay. Now, we also know from combinatorial optimization that an LP has many, many, many equivalent formulations. Any of you who has seen max flow min cut, you can probably write many different LPs which try to capture the same thing. Now, the question is, which one of these would you choose to solve a particular problem? And that can have profound impact on what solution you actually get. If you think about it, and in the context of this workshop, big data is about finding approximately optimum solutions, because finding the exact optimum might just be very hard, or you may not even be interested in it. It may not be relevant. Now, we've always seen that things are equivalent to each other, and therefore two formulations are equivalent. The proof of equivalence you would always see is equivalence at optimality. That does not say anything about a particular approximation solution. And this is the key point which would be the start of this talk. And this is a fundamental question, because if we step back and say that we will only solve these problems approximately, that opens up a completely new can of questions. And hopefully I will convince you towards the end of this talk that succinct representation has something to do with efficient optimization. Now, we said there are many different equivalent formulations of a linear program. What is the most basic notion of equivalence that would come to your mind? Anyone? A primal or a dual formulation? We all know that using strong duality for linear programs, these two things are, to some extent, combinatorially describe the same structure. You have complementary slackness. You have so many different tools. But suppose I solved the primal linear program approximately. What do I know about the dual? Nothing. And I would sort of impress upon you that, or try to, that depending on the problem you care about, you may be better off starting from the dual of what you wanted to solve. So this talk would be about resource-constrained computation, and particularly models in which you cannot just enumerate through all kinds of constraints, validate all of them, in particular, complementary slackness conditions. And the reason, the particular example I will choose, I will make sure that there are exponentially many constraints in the primal or exponentially many variables in the dual, so validating complementary slackness condition is just simply infeasible. The particular problem is maximum matching. I would just, for this talk, compare cardinality, maximum cardinality matching, and I would just consider non-bipartite graphs. Cardinality matching in bipartite graphs is really simple. However, weighted bipartite graphs are not simple. I would not be talking about weighted graphs in this talk. There are some results in the paper. So before I proceed further, what is a model I would be talking about? And this is big data, so I would talk about the semi-streaming model. I don't know if this was defined in the boot camp. So I have a graph with n nodes and m edges, and m is much, much larger than n. Otherwise, you could have just stored the graph and you're done. I see the definition of semi-streaming being little o of m edges, that you cannot store all the edges. There can be other definitions. Some people prefer n polylog n. I don't see a difference between n polylog and n to the 1 plus little o of 1, as long as both are much less than m. The format of the input would be a list of unordered edges, and you would make few sequential passes over that list. It's a standard streaming model. The point I want to say is the streaming model in itself is not the most exciting thing in the world. But what it lets us do is really interesting. If you have sort of heard through talks, for at least the first 2 days were very heavy on streaming. If you think about the techniques that came out from looking at problems through the lens of streaming, those techniques are far more interesting than the models themselves. And that is the single most reason we should study the semi-streaming model. This particular result will be about adaptivity and access to data. I'll come to that in a second. The particular result I would show you is that in this kind of a world, in a semi-streaming world, I can compute a 1 minus epsilon approximation to the maximum cardinality non-bipartite matching using p by epsilon passes, n to the 1 plus 1 by p space, and that running time, where p is some constant. If you think p is like 10, the space requirement is n to the 1.1. It's almost linear. And the nice thing of choosing this notion of p is any polylog factor can be simply absorbed in the polynomial term. It just makes your writing much, much, much simpler. Okay, so that being said, one of the reasons I've already said that, the reason for looking at streaming is good streaming algorithms give us good algorithms. And it should be somewhat obvious, but the algorithms I will present to you will be of the following form. They would use what Andrew talked about as homomorphic sketches or homomorphic computation. They would involve taking inner products, and that's where the running time, the dominant term of running time will come from. And I will assume once the inner products are computed, some central server can do computation in almost linear time and space. As we have heard through this workshop, sketching or inner products would allow you good dynamic graph algorithms. Andrew talked about this. And we've also seen if you can do sketching or inner products, you get good parallel algorithms. So except the point 2, this sounds like a lot of interesting things can be done. And I also think this model of what can you compute given a few sketches of a data is a fundamental question in its own right. And it reminds me of the compressed sensing or compressive sensing models. We saw a talk of cloud computing. This is a very natural model to ask questions. That brings me to MapReduce. Everybody has their own MapReduce definitions. I may or may not have one of them. I believe any reasonable model of computation should allow the points 1 and 2, which are up there, because if you do not have a central server which cannot do it, which is so weak, then you probably need a bigger board. But there is a lot of discussion on MapReduce. Your mileage on this may vary. So without further ado, let me get to the main result. To recap, I'm going to talk about a problem where you're given a list of edges. You can compute sketches, inner products. And I would ask the question, how many rounds would you need to solve the maximum matching problem to 1 minus epsilon approximation for any given epsilon greater than 0? Okay. The key and what is most exciting to me of this talk would be the following. I will not improve the number of rounds. But what will I do? I will impress upon you that the number of rounds which need to depend on each other is small. And therefore, the only time I would need to access data would be much smaller than the total number of iterations. And that is an interesting angle in itself. So this is the standard LP for matching. So any questions about the plan? It's just too early in the morning. Okay. Since it's too early in the morning, let's begin with a linear program. This is non-bipartite matching. It's a standard definition. This is exactly as in all textbook you would see. I define a set of odd sets where this is the cardinality of U. That's a very natural definition. And this is my linear program where Yij for an edge ij is in an integral solution the indicator variable whether ij is in my matching. If it is 1, otherwise it is 0. And when I write a linear program, it is a fractional relaxation of it, and the constraints are, the constraints are each edge is matched at most once. And this is the classic odd set constraints, which rules out that if you have a triangle, you do not select all edges of the triangle with weights half, half, and half. Because then you would think you have a matching of size 3 by 2, but you cannot get a matching of size more than 1. And in fact, if you ignore these odd set constraints, you cannot have an approximation better than 2/3. Okay, so this is the standard linear program, and this constraint is written for all odd sets. So this is exponential. There are exponentially many constraints here. Okay, now I want to do a 1 minus epsilon, 1 minus 2 epsilon approximation. So what should I focus on? I don't have to solve the huge LP for that. For that, it turns out that if I restrict my odd sets to a size of at most 1 by epsilon, then the relaxation is a 1 minus order epsilon approximation to the original one. The reason is that if you see for very large odd sets, the gap between this and this side, assuming these constraints are tight, would be something, say cardinality of U is 11. So on the right-hand side, you would have 5. And on this side, you would have 5.5. And so this gap will shrink if you look at larger and larger sets. So if you're interested in 1 minus epsilon approximation, it suffices that you just subsample or throw away all the other constraints, and that's a linear program you want to work with. So questions about the linear program at this point? Okay. So what's our plan? We want to solve this linear program, and once I get a solution to this, I will round this linear program and construct a matching. Rounding, we've always done rounding. We can round anything that moves. I'll not talk about rounding in this talk. What I will talk about in this talk is how to solve that LP approximately. Okay. Now, approximately solving LPs has been an incredibly rich research enterprise. It's a never-ending road. It's a very exciting road. All of these techniques eventually, at its heart, boil down to some kind of an exponential weighted gradient descent method. And this has been not just in theoretical computer science community, this has been invented in many different communities. And just the incomplete list of what I could think of in sort of theory CS, and theory has many different connotations here, are these people, and some of them are also in the audience. Neil Young is here. And there has been an incredible amount of research on this. I would point everyone to the survey by Aurora Hazan-Kale in Theory of Computing. They describe a very comprehensive history of this problem. I am going to talk in this particular talk about the two methods, multiplicative weight update method and a modification of it, fractional packing and covering, and sort of use those ideas. Okay. So what is the canonical setup? I want to solve that LP. In particular, for the cardinality matching, the vector C is all ones. The X is actually the Yij you looked at. These were the packing constraints that every vertex is matched to at most one edge, and the odd sets do not have too many edges. So instead of solving that problem, I would say, modulo slipping a few details under the rug, I need to solve this decision problem. If you think about it, I wanted a maximization. I just said, let's just figure out if there is a feasible solution which is large enough for particular assignment of beta. And I will keep raising beta, and at some point that should give me a near maximum solution. Okay? Okay. Now, all these methods, not all, but most of them which have better convergence assume that you're given some sort of a weaker approximation. And you saw some talks yesterday about how to recursively refine polytopes and get better and better solutions. So we'll assume we are given a ballpark polytope P, which is easy to optimize over. And the important parameter there would be this notion of rho, which is the width. All it says is this ballpark polytope, where it's easy to solve the problem in. If I pick any point in that polytope, this number, you can think of this as a condition number, is not very large. And this will control the convergence. Okay, with that definition, let's see the multiplicative weight update method. So imagine your ballpark polytope is this very large circle. In the actual feasibility region you are interested is the shaded circle. Now, what we would do is at any point of time in the multiplicative weight update, you would look at a particular direction of optimization, and then you would look at the plane which is normal to it. And the question which would be posed to a helper or an oracle is the following: give me a point which is on the same side as the feasible region along this direction. So if the red arrow is my direction, I look at the hyperplane which is perpendicular to it. I want a point on the same side of the hyperplane as the feasible region. Okay? It's a very simple task, so I get this point. Now, given this point, if that point already satisfies everything I want, I'm done. If not, I get that some constraints were violated. The direction I'm now interested in changes. And this is where the exponential update of the dual weights come in, and the direction changes using, the direction is just multiplication by 1 plus minus epsilon. Okay, now I have a new direction, and I have a new oracle query, and the oracle supplies me a new point. And so this goes on, third, and after a bunch of iterations, I have a collection of points. They're all over the place. But the fascinating thing is, if I now take the average of all these points, I'm approximately feasible. So the multiplicative weight update method is really, really simple. This is exactly this picture. Okay. So what do we know about this? There's a long history of this. We know that the dual weights change slowly. What are the dual weights? Dual weights are this direction. If you look at a primal problem, whose feasibility you want to solve, the red arrow is a particular assignment of the dual variables, which need not be feasible, by the way. And these dual variables change slowly, and the problematic aspect of multiplicative weight update method is the directions are based on the violations of the point which you compute at every step. This is not particularly a great point. We have just seen that the final solution is the average. So the overall number of rounds one needs is rho epsilon cube log m. This is in Aurora Hazan Kale, where m is the number of constraints. And I'm assuming that you can compute these and maintain these exact dual weights. So what would happen if I apply multiplicative weight update method to the LP which I said I wanted to solve? The first thing, the primal which had many, many, many constraints. There were exponentially many constraints corresponding to the odd set. That means there are exponentially many dual variables. You just cannot run this. That's one. The second is the optimization direction depends on the history. That's another problem. So let me now switch gear and talk about fractional covering and packing problem. It's very similar to the multiplicative weight update method. And let's even see what happens there. So in fractional covering and packing, I would start with a feasible point, or in the weaker polytope. And I would try to get to kind of move around and get to the shaded blue region, which is my feasibility region. Okay, so what fractional covering does is again assigns a dual weight exactly by the same formula, or almost the same formula. Now, instead of thinking about hyperplanes, think of the following operation. Take the point where you are and take the improvement direction and ask the question, how far can I go in the weaker polytope? Okay? Suppose you can solve that optimization problem. That's why you choose the weaker polytope, because the optimization is easy. So you get this black point, the second black point. Now you say that, okay, that's as far as I can go. If I go that far, clearly I'm at the end of my weaker polytope. That's not a good thing. So I will make a small step. I will only go a little bit. And then you'd stop. So the red point is where you will move to. And then that's your new point. Now you'll update your dual weights. Very similar process as before. You would again compute the direction. And you would again find the extreme point as far as you can go. You would again take a tiny step. So if you can see that you're kind of spiraling into the feasibility region. This is these two, multiplicative weight method and the fractional covering and packing, are very similar. Where they differ is how you analyze the convergence. So think about what's happening is you can analyze the step size. You get to control it. And if you think of the feasibility region and concentric rings around it, if you are very far away, you would take very large steps. If you are very close, you will take very small steps. And once you kind of, let's keep this. Once you kind of do that, you can shave an epsilon off of the convergence parameter. It becomes rho times epsilon to the -2 log m. And this actually has a lot of advantages. However, here is something, both of these, either multiplicative weight update method or Plotkin-Schmeier-Stardosh, you need to compute explicitly the maximum violation. So consider the following problem, how easier it is to solve. I give you a collection of edges, and I say that this is the maximum matching. Can you find me the constraint which is maximum violated? This is a non-trivial problem. And this is the minimum odd cut problem. And the best known result is a super quadratic at this point. OK. So far, it seems all the methods we are looking at, the number of constraints is exponential. Finding the maximum violation is hard. Even finding the sign, are constraints violated or not, is pretty hard. And if you think about it, what is happening underneath all these primal dual algorithms is a certain concentration measure kind of argument. I'm increasingly becoming more sure that I'm feasible. And so 1 by epsilon square log of the number of constraints is a very natural measure for that. So how do I get past this? To solve matching, I need to do something where capital M is n to the 1 by epsilon. So this is not great. So as I said, I will show you that you do not have to access data, but what we would do is we'll start with the dual. And this is why I would say that this is a dual primal algorithm. So what is the dual of the matching problem? The dual of the matching problem, exact same problem which I wanted to solve. You now have a variable, x sub I, which is for vertices. And you have z sub u. These are the variables which corresponds to the odd set which you had before. and if you believe that I can take a dual, the dual looks like this. But something very nice happened here. Instead of exponentially many constraints, I now have polynomially many constraints. I have a constraint just for each edge. So that's something very nice. I, of course, have exponentially many variables. We'll find a way of dealing with that. So the number of constraints is m. The dual-primal method, my weaker polytope, I would define, is this. If you think about this, that I want a solution which is minimum, I would want this to be at most better, and I would want all the edges to be covered. So far, nothing exceptional has happened. Okay, now what is the width of this polytope? If I do not say anything else, the width is actually huge. So keep that thought in your mind. Now, the rest of the algorithm is kind of best explained in a tongue-in-cheek way by an Elenchus. And this is something which works very well with graduate students, or not always. So I, as the algorithm, I will say that this graph surely has a small cover, where cover is the dual which you just saw in the previous page. You clearly are not going to have any of it. You just think I'm out of my mind, and you're going to say, no, no, of course not. Here is a matching. And now you use weak duality, therefore you cannot have a small cover. And what I would say, thank you very much. The matching is what I wanted. And this is exactly how the algorithm will proceed. So the difference is in multiplicative weight update method or the fractional covering and packing, which, as discussed, what was happening is you wanted a primal solution and you were managing these dual weights. Here, I am actually going to ask the oracle to provide me the final solution, and all I would construct is a certificate that the dual is infeasible or feasible at some point. So the matching will be provided by the oracle. Now you can ask that, okay, you haven't changed anything. So how are you getting any benefit? The benefit is, if you think of this oracle and an algorithm approach, the resource constraints of the oracle are different from the resource constraints of the algorithm. And that is what we can exploit. So this is the rug part. Now, as I said before, you can slowly raise beta and in powers of 1 plus epsilon, and it works out. Okay, we just talked about this. So let's look at how we solve this dual of our matching problem. I am going to run a primal dual on this dual. That means I would need, that means I would need to sort of maintain a list of weights, uij. Keep in mind that uij is now corresponding to every edge in my graph, and there are a small number of weights. What all these multiplicative weight update or fractional covering, what you saw, the auxiliary problem which I need to solve is this, that given a set of weights, which was here, multiply those constraints by uij, just add them up. So instead of solving m constraints, you reduce the m constraints into one constraint. So you recursively solve this one constraint subject to the weaker polytope. Is this clear? That from an m-dimensional problem, I've just reduced it to a one-dimensional problem. And that's why these things work. All right. The quantities uij can be computed using a pass. I won't talk about it. These are easy. They're very easy, actually. Now think about this optimization which I've asked you to solve. The uij can also be done by MapReduce. Forget how Oracle stores them. I will use a cut sparsifier. Think about the problem the Oracle has to solve. It has to solve these two constraints. What does this remind you of? It's knapsack. It's just knapsack. All I'm doing is I have some sets which have some weight, and this is my profit, and I want large profit subject to a knapsack constraint. It's it's as simple as things get. So it's a two-constraint problem. Now, what I would do, and here is where the whole dual primal thing works, is you give me the weights uij, I am going to rescale them and define yij. And I will interpret these yij as the variables in an original matching LP. Then my task would be to look for a collection of odd sets or vertices which gives me the best solution for the knapsack. It's a really simple problem. Okay, how do I solve this? So what I would need is look at these tight sets for which the odd set constraints are violated, and I will just find a maximal disjoint collection. I will need to use something which is approximate Gomory-Hu trees. It can be done in linear time. I won't get into it. I just need approximation. Okay, so suppose those odd sets look like that, and they can be like all intersecting in some small set. Suppose since I'm finding a maximal collection, I find that one purple set which intersects everything. Okay? So far, so good. Now I have two cases. It's a very simple proof from now on. I have two cases. The collection which I have found has a lot of mass interpreted in this new variables yij. If it does, then it's very simple. If it doesn't, that's the second case. If it has a lot of mass, I can just pick those sets, and I can pick them by a very large amount, by 1 by epsilon, even though that doesn't make sense. It doesn't make sense to set xi to 1 by epsilon, but if I do this, I can satisfy those two constraints. And that would be sufficient for my primal dual framework to work. What is the other case? The other case is the maximal collection which I found has very little mass. The solution is very simple. Just go ahead and delete them. Because you found a maximal collection, every problematic constraint has been eliminated in your solution. You now have a feasible solution. And this is where I am getting the oracle to actually give me a matching or a fractional matching. Is that clear? I make it a knapsack. The task for the oracle is to give me a collection of odd sets with sufficient mass. If it cannot, if it just were to delete those subsets, it already has a fractional matching. And that's it. There are issues that you need to represent this in a compressed format and all this, but it works out. So what is the long story? If you look at this, each variable xi and zu gets weight at most 1 by epsilon. It's easy to see that the width is 1 by epsilon. It's just algebra which says that the width is 1 by epsilon. And if you sort of work out the entire math, this gives you total these many rounds. But the algorithm is really simple. I would now improve this algorithm. Okay? So the algorithm literally needs to solve knapsack and just collects a bunch of odd sets. Okay. Now, this is my width, and the width is 1 by epsilon because, by the way, there's one, I said that I will choose a collection of disjoint odd sets. It's the disjointness that lets me bound this sum. If I did not choose disjoint odd sets, I'd have a problem. Okay. Let's see. Okay. So what is the algorithm doing? This is a recap. I'm just collecting disjoint dense cuts of size 1 by epsilon. If you care about a MapReduce implementation, all you need is every edge gets to know the set it is in, and that's a very simple hash. These sets are small. That is the key point in all of this. Okay. To improve the algorithm which I talked about from 1 by epsilon cube log n all the way to 1 by epsilon, we'd need two ideas. The first idea which would be the following, I would use something which is known as total dual integrality. What this says is, assuming the edge weight is an integer, for an optimum solution, the dual of a matching polytope, that quantity is an integer for every vertex. And these optimum dual variables are also, they define a laminar family. This is a fantastic result, and this has been proved since 1978, and a history of incredible research has gone into this. This is used in kind of the minimum odd cut algorithm, finding the minimum T-join. But as far as I know, this is the first explicit use of these inequalities to solve the linear program. The previous uses of TDI were implicit in the sense that they said that there exists a minimum odd cut and we should go find it. I would actually write those constraints down and satisfy them. There are a few problems. The total dual integrality is proved for all the odd sets. I'm not looking at all the odd sets. I'm looking at all the small odd sets. So that changes things, but I would now need to look at half integral solutions, and I would guarantee something like this. It's a little bit weaker than total dual integrality, but it's pretty much the same, that this object is less than 2 times capital lambda for all lambda greater than or equal to 1. What would happen is, this is the LP I said I would solve. I would just stick this constraint into my polytope, which I said was the easy polytope. What would that do? If you now look at this constraint and stare hard at this constraint, the width of my formulation is now a constant. And that would take care of one factor of epsilon. The feasibility holds for some parameter. The algorithm provides some other parameter. That's not an important thing. But here is one thing which goes very wrong. And everybody thinks this is easy till we come to this slide. If you add constraints to a primal, your dual will change. So if you started with the matching dual, you started with the matching problem, and then you added these constraints, you now have a more crazy but equivalent formulation of the matching problem. And the solution you will get is to this problem. So it's an interesting task for, or puzzle for you, that if I give you a feasible solution to this problem, how will you go and extract a matching? And this is what I see as most exciting here, that you just can't throw in constraints, even though it's very nice, because then you'll have to kind of pay for it later. So it's not obvious how to get a matching from this, but again, we can round. And this is rounding here is from one fractional solution to another fractional solution. We can do this. So we won't worry about this. So what happens? So using total dual integrality, I can prove my width is low, but I still have to solve this problem. Keep in mind the collection, what I said, you're collecting odd sets. That will not satisfy this. So how will I solve this problem? I'm going to recurse. That means at an outer level, I would solve the problem which is on the slide. At an inner level, I would use 1 by epsilon rounds without this constraint. It will not matter to me because the inner level is going to work on a very, very sparse graph. That is the key here. It's the outer level which will only have to access the edges. Once I do this, I get, finally, after all this, 1 by epsilon square log n rounds. Now comes the next main idea, is that all these primal dual algorithms, the dual weights change slowly. In fact, they change by 1 plus minus epsilon. Therefore, if in t iterations, the weight also change very somewhat small. Now, if I can define a following problem, a deferred sparsification problem, where you're given a promise that the edge weights will be within some range. So you construct a data structure D such that after you have constructed the data structure, the exact values are revealed. If I use this, here is what I can do. Given the time, let me speed up a bit. What I would do is I would construct T different data structures simultaneously and independently. I would use the first data structure D1 to solve my first iteration of the problem. After I have solved the first iteration of my problem, my weights Uij for the second iteration are now revealed and completely specified. I would now use D2, but I will not need to read the data again. This is the deferred specification, what is buying me. So I would construct T such specifiers simultaneously. I would use D1, use the result on D2, use the result of D2 on D3, and I would do this cascade for T rounds without looking at data again. Now, if I set the parameters right, T becomes something like 1 by epsilon log n, and the total number of rounds in which I need access to data would decrease from 1 by epsilon square log n to 1 by epsilon square log n divided by this T, and everything works out to order P by epsilon passes. So to recap, here is what we did. We started from the dual of the matching problem. We added additional constraint based on total dual integrality. We now ran almost a standard primal dual algorithm where we generated dual of dual weights. We interpreted those dual of dual weights as the inclusion in a matching and used deferred specifiers on that. And using that, we decreased the adaptivity across the iterations. The task of the oracle became generate either a primal witness, either find me a matching, or prove a bound on the primal. So somewhere, the match, instead of me constructing a matching problem, I got the oracle to actually give me the solution. There's some details in all of this. This all needs to go on simultaneously for all beta. It works out. And in this method, what is really critical, that the structure or the representation of the dual polytope was critical. The entire proof works because of these TDI constraints, which bound the width. And this is very exciting, and it takes me back to approximation algorithms. Those of you who are familiar with primal dual approximation algorithms, it's the structure of the dual problem which is more interesting for such a primal dual approximation algorithm, because you construct a feasible dual solution, and then you kind of try to get an integral primal solution out of it. So it's the feasibility of the dual which is the critical point, and the structure of the dual helps you get a better algorithm. So that's pretty much all I had to talk about. You heard about matching. There are lots of exciting history, structure, and I see matching as a canonical combinatorial optimization problem. In a companion paper, which is also in archive, we considered weighted capacitated B matching, and we gave the first fully polynomial time approximation scheme for that problem. To me, this is a tip of the iceberg, and we've just started understanding fast and approximate solution of combinatorial optimization problems. Those of you who have followed the recent work on electrical flows and solving max flows faster, that's another instantiation of very similar phenomenon. And finally, in the context of big data, there is hopefully not a big divide, which is, do you see your problem as a big vector problem or a big graph problem? In all of streaming, we always see all this estimation of statistical quantities, frequency moments, norms. These are, to me, big vector problems. I am very excited about graphs, and structure is probably best encoded using graphs. So it's a natural open question for what kind of big graph problems can you solve in these resource constraint models. That's pretty much all I had to say. Thanks.
Do we have time for a quick question for Sudipto?
Sure. So the question which Neil asked is, can I summarize where I managed to decrease the adaptivity? It came from the following thing. I would still run an algorithm which takes 1 by epsilon square log n iterations. However, what I would do is in one shot, I would construct 1 by epsilon log n data structures. And each of these data structures will provide me a corresponding dual weight for that iteration, but I would not have to go back to the data to construct them again. So it's a deferred problem. It's a delayed evaluation problem because I have this promise that the weights are within some range. Yes, so I can only do this because I have something which is a cut sparsifier, and those of you who listen to Andrew's talk, I can construct this cut sparsifier using sketches, and if you stare hard at that algorithm, it turns out that it's an oblivious algorithm because it's a sketch-based algorithm. If I just have a guarantee that the weights are within some range, the algorithm will work just fine. That's what I'm using.